Okay, in this video, we're going to look at radioactive decay and the use of the half-life of a radioisotope. So we have radon here. So we want to know how long it would take radon to decay to 1/3 of its original amount. And we have the half-life of radon as 3.83 days. We can write down what we have here, and it looks like all we have is the half-life. So that is going to be 3.83 days. So we don't have the amount of what, right? We know that it's radon. The radioisotope of radon is 222 radon, but we don't have like a mass or whether this is the activity or the number of nuclei, and it doesn't actually matter. So, and I'll show you why in just a second. So radon is something that is a radioisotope that's found sometimes in people's basements or homes or other buildings. And because it's radioactive, it can cause damage in the body because you can breathe it in, and that will eventually cause lung cancer. And it's actually a really big cause of lung cancer. So often we'll get detectors in a house to test for radon. So let's look at the equation for radioactive decay. So we can say N, this is the amount of the radioisotope, in this case radon. So N of T, and that just means that N is dependent on time. So the amount that has not yet decayed depends on time, and that's equal to the original amount, we call that N naught, times e to the negative lambda t, where t is the time, and lambda is the decay constant. So this is the decay constant. And that is equal to 0.693 over the half-life. So 0.693 is actually the natural log of 2, so that just has to do with how it's derived, but you can just put in at 0.693. So for radon, the decay constant is going to be 0.693 divided by 3.83 days. Now, you can use different units for this, but in the end, whatever units you use, that's also going to be the units of the time that you're solving for here. Now, if you're originally given the time in, say, seconds, and you're trying to find the amount that's left instead of the time, then you'll need to make sure your units are consistent. So you'll need to change the half-life to seconds if you have a time in seconds, or change them both to days or years or whatever the units are. They just need to be consistent. Okay, so our decay constant for radon is going to be 0.1809. And we have units of days to the negative 1. Now that just means it's in the denominator. Okay, so now let's look back at our radioactive decay equation. We want to know how long it takes for the original amount, N naught, to decay to 1/3 of its original amount. So we want N of T to equal 1/3 of the original amount, which is N naught. So we can now plug this into the first equation. So that's 1/3 N naught equals N naught times e to the negative lambda t. All right, and as you can see here, we have N naught on both sides, and these are just going to cancel out. And that's why you don't actually need to know the amount in a case like this. So that just cancels out. You divide through by N, and it's gone. And now you just have 1/3 equals e to the negative lambda t. So N of t, or N naught, can be the mass, so the original mass of radon that you have. So it can be the mass of radon 222, or it can also be the number of nuclei. It can also be the activity, A. So if you're given units of either mass, or that you're just given the number of radon nuclei, or the activity in disintegrations per second, any of those can be used for this N of T and N naught. But of course, they have to be consistent, but the equation works in any of those cases. I hope that makes sense. But in this case, it doesn't actually matter what it is because N naught cancels out. And no matter how much we have, we know that we're just looking for the time it takes for it to go to 1/3 of the original amount, whatever that original amount was. And it holds for the original activity, the original mass of radon. Of course, that mass is still there, it's just decayed into something else. But what we would be solving for would be the mass of the radon nuclei. Or it can just be the number of radon nuclei left that haven't decayed yet. So let's go ahead and move on here and solve for T, right? So let's take this equation. And what we're going to do to get, we want to isolate T. So we're going to take the natural log of both sides because we want to get rid of the exponent. So that's going to give us natural log of 1/3 equals, so when you take the natural log of E, it's just going to give you what's in the exponent. So that's negative lambda T. Okay, so we just want to solve for T, right? So that's going to be T equals the natural log of 1/3 divided by negative lambda. And natural log of 1/3 is actually negative 1.099. And we're dividing that by negative 0.1809. And then we have days to the -1 in the denominator. That's actually just going to make it go into the numerator, so we'll get units of days here. Our negative signs cancel out, so we get a positive time of 6.08 days. I've rounded it to 3 significant figures since our half-life is originally given in 3 significant figures. So 6.08 days, and that makes sense. It should be more than 1 half-life since we've got less than half of it left. So our time it takes for us to get 1/3 of the original activity or 1/3 of the original radon nuclei that have not yet decayed is 6.08 days. So hopefully that makes sense. Let me know if you have any questions. And of course, this will work for any radioisotope. They would just have a different half-life, and then that would make it have a different decay constant. So hopefully that was helpful, and thanks for watching.